Now there's some systems of equations where the two lines, if we were to graph them, so if we have a coordinate plane here, if we were to graph the two lines, they end up never intersecting. They're parallel. And so that means that there is no point, there is no xy coordinate pair that works as a solution in both of the equations. So without graphing, we should be able to determine that circumstance as well. So I want to demonstrate that here. So if we look at the system of equations that we have here, we could use some substitution maybe in this top equation. Getting the x by itself wouldn't be too bad. So I think we could do that. Or we could go ahead and multiply that top equation by, let's say, 4 in order to get a match on the x. And as it turns out, it'll be on the y as well. So I think we'll take that approach on this one. We'll go ahead and multiply this top equation by 4. Get the x's to match up, even though they'll be different in a positive and negative sign. So this top equation is going to become 4x plus 8y equals -4. And then the bottom equation is just going to stay put. -4x minus 8y equals 2. And so now, if I add those equations together, what we're going to find is not only are the x's going to disappear, but we also are going to get the y's to disappear. So that means there's nothing left over here when we're done adding these two equations. When you have nothing, you have 0. But on the other side, we have -4 plus 2, which is -2. And so in this circumstance, we had all of our variables disappear when we tried to combine the equations into one, but we ended up with a false statement. 0 does not equal -2. And so that is an indication that this system of equations, if we were to graph it, would end up with a couple of parallel lines. And so we say in this circumstance that we have no solution. We just put the 0 with a slash through it. There's no answer. There's no point of intersection between these two lines. There's another circumstance that can occur, and that's where the lines don't intersect in one point. They're not parallel, but instead the two lines are on top of each other. The two equations turn out to describe the exact same line. And so in that circumstance, the points are touching in an infinite number of locations. So we want to investigate what that looks like when we solve via algebra, and then how do we write the answer in that circumstance. Because it's not just all real numbers like we often put when there's an infinite number of answers, because it's got to still be the points that are on the line. Like a point that's over here or a point that's over here is not on that line, so it would not count as a solution. We need the points that are on that line right there. But we'll get there in a second. So I need to take, in this case, I've got the y isolated, so I'm going to substitute it into this second equation as follows. So that top equation is going to be 5x minus, now it's got to be careful here, I have to put what I'm replacing y with in a set of parentheses, so it's going to be 5x minus 5x plus 6 equals -6. Because now I have to distribute this negative sign into both of these sets of parentheses, or into the set of parentheses to both pieces. So we've got 5x negative, think of it as like a -1 times 5x, so we get -5x, and then -1 times 6 is -6. So then we get -6 on the other side still. And so here we can see our like terms, 5x minus 5x, are going to cancel each other out. And so this time, unlike the one up above, we've got a true statement after all of the variables have disappeared. So once again, we did everything right. We used our substitution, we plugged into the top equation, but then when we tried to solve for the one remaining variable, it got canceled out as well. But in this circumstance, we ended up with a true statement. -6 does indeed equal -6. So that's the signal to us that what's going on if we had graphed it is that the two lines are on top of each other. But how do we write the answer in that circumstance? Like I said, we can't just put all real numbers, because we have to somehow communicate that it's only the points that are on that shared line. And so the way we're going to do that is we're going to say it's all of the points x, y. So we're trying to communicate that it's a whole bunch of ordered pairs. It's every ordered pair. It's every xy coordinate that works in, and then we're going to write either of the two equations. So I'm going to go ahead and pick the top one here just because it's first, but I could have just as easily written the bottom one because that is the exact same line. So what this answer is saying is it's any ordered pair, any coordinate that works when you plug it into that equation that we see in front of us. And so we want to close things out here in our notes with an example of how we can write a system of equations to help solve an application. So in this case, we're told that the perimeter of a rectangle is 24 centimeters. So I'm going to go ahead and draw a rectangle for myself. So I'm going to say here the perimeter is 24 centimeters. And then we're told that the length, so right here we'll say is the length is twice as long as the width. So we'll deal with that twice as long piece in just a second. And so we eventually want to find the length and width of this rectangle. So in order to solve this problem, we're going to seek to write two equations. We're going to use a system of equations to solve. So the first thing we got to do is we've got to do what I call defining our two variables. So we want to write down what are the variables that we're going to use and what do they represent. So in this case, I'm going to say W is the width and L is our length. I could have used X and Y, I could have used A and B. I like to use variables that are going to be descriptive of what they represent so I remember when I get to my solution. So now I've got to write two equations. So the first sentence says that the perimeter of the rectangle is 24 centimeters. Well, how do we find the perimeter of a rectangle? We add up all the sides. Well, and in a rectangle, the opposite sides are the same, so we've got the two widths on either side, we've got the two lengths on either side. So all four of those lengths have to add up to equal 24. So I could keep them all separate, or I could recognize that I have two widths, so 2W, plus my two lengths, 2L. That has to add up to equal 24 centimeters. And then I'm going to use this second sentence to write my second equation. So it says that the length is twice as long as the width. And so I'm going to kind of translate that as I roll through that sentence. The length is, so length, we're using L, is in a sentence translates into an equal sign, so L equals, and then it says it's twice as long as the width, so that just means it's 2 times W, and so there's my second equation. And so now I'm set up in this case to use one of our two algebraic techniques that we have worked on, substitution. I've got L all by itself here, so that means in that top equation I can go ahead and take L and replace it with that 2W. So we've got 2W plus 2 times 2W in place of the L equals 24. So now we've got 2W plus 2 times 2W is 4W equals 24. So that's 6W equals 24. So then we can divide both sides by 6. And so we get W equals 4. And so then we're asked to find both the length and the width. So we have found the width is 4 centimeters. That's supposed to be an M there. Let's try that again. And then we can plug into either of these two equations to figure out the length. I would definitely choose the second of those two. And so we can say that L equals 2 times W, so 2 times 4 is 8 centimeters. So we have found the length and the width. So we define two variables, we write two equations, and then we solve that system of equations.